Hi everyone, my name is Kyleigh Quillian, and today I'll be presenting my Physics 2211 Lab 2 report on the motion of a falling object. In this lab, I tracked the motion of a stuffed buzz and compared its row movement to two computational models in GlowScript, one with drag and one without. The purpose of this lab was to observe the motion of a thrown object and analyze how gravity and air resistance affects its trajectory. I recorded the motion of the stuffed buzz using Tracker and then simulated the same motion in GlowScript using two different models, one with drag force and one without. The goal was to see how closely each model matched the actual observed data. This lab is based on three main physics ideas. First, Newton's second law, which says that the change in momentum is directly related to the net force acting on an object. Second, gravitational force, which pulls objects downward with a force equal to mass times gravity in vector form, that's negative mg in the j-hat direction. And third, drag force, which is a resistive force caused by air. It always acts opposite the direction of motion and depends on the square of the velocity. In vector form, is written as negative b times the magnitude of velocity squared times the unit vector of velocity. Together, these principles form the foundation for the two models that were built. For the real experiment, I threw the stuffed buzz toy and recorded its motion using the Tracker software. The system in this setup is the stuffed buzz itself. The surroundings are the air, gravity, and environment around it. Tracker allowed me to get position and velocity data from the video, which I later compared to my simulations. I created two GlowScript models using the same initial conditions from Tracker. On the left is the no-drag model. The only force acting here is gravity, so the net force is mass times gravitational acceleration, and the drag constant is set to 0. On the right is the model with drag. Here I added the drag force term using a drag constant of 0.005. That means the net force becomes gravity plus the drag force, which opposes motion. These two setups let me directly compare how including air resistance and changes the predicted trajectory. The graph shows all three trajectories on the same plot: the Tracker data from the real experiment, the no-drag simulation, and then the drag simulation. You can see that the no-drag model rises higher and lands sooner, while the drag model drops off faster and lines up closer to the real path. The Tracker data clearly doesn't follow a perfect parabola, and the drag model reflects that better. When we look at the velocity versus time graphs, the difference becomes even clearer. In the no-drag model, velocity decreases in a straight line because gravity is the only force acting and acceleration is constant. In the drag model, the curve bends downward because air resistance increases with speed and reduces the net force over time. Even though the motion doesn't last long enough to flatten out, it still slows more quickly than the gravity alone case. For the what-if question, I considered what would happen if the same object were thrown straight upward instead of forward with the same initial speed. In that case, it would stay in the air longer because gravity would slow it to the 0 first. Then it would accelerate downward again since it has to travel both up and down. The total time is greater than in the original throw. The total time in that case would be 2 times the initial velocity over g. In this experiment, I confirmed that without drag, an object follows smooth ideal motion under constant acceleration from gravity. When drag is added, the object slows down more quickly, and that made the drag simulation match the real Tracker data more closely than the no-drag model. Sources of error could include tracking inaccuracy in trackers, estimating the drag constant, and the fact that the stuffed buzz doesn't have a streamlined shape. A smoother object might behave differently in the air. To improve accuracy, I could repeat the experiment several times and average the results, use a higher frame rate camera for motion tracking, or test different objects to compare how shape and drag influence motion. Thank you all for listening.